quand même fatigant pour du masque.
Ouais. Alors, restons.
C'est pour ça qu'on va rester tout le temps, on va parler bien, on est obligé.
Oh, j'en ai marre. On pourrait se mettre debout pour suivre les autres.
Ouais. Vas-y, je t'en prie. Je peux faire aussi du chiton, si tu veux. Ça, c'est bon.
Okay, very good, Daniel. We'll probably start. So, welcome everybody. It's my pleasure, great pleasure to introduce Daniel Stern from Chicago, and he'll give a lecture on harmonic map methods in spectral geometry. So please, Daniel.
All right, so first of all, thanks very much for inviting me to speak and for doing such a nice job getting the hybrid format to work. It's a little strange, but it beats nothing, right? Okay, so yeah, I'm talking about some use of harmonic maps and some classical questions in spectral geometry and some more modern questions as well. And everything I'm talking about is joint work with Mikhail Karpukhin at Caltech, and some of it's also joint with Mikhail Nahon and Iosif Polterovich at Montreal. Okay, so let's get started with something classical. All right, so our setting's pretty simple. We're working on a two-dimensional surface. So if we have a closed two-dimensional, let's say Riemannian surface, then we're going to be thinking about the positive spectrum Laplacian, right, whose spectrum is this classical sequence of fundamental geometric invariants. Right? Okay, so if we rescale those invariants by the area, then we get a scale invariance sequence. All right, and we can ask about trying to do some sort of variational theory for these. Okay, so what could we try to do? So it's not hard to see that in any given conformal class, we can always find a sequence of metrics which makes any given eigenvalue tend to zero, any given area normalized, so scale invariant eigenvalue. So for instance, if we're on S2 and you want to make the first normalized eigenvalue go to zero, you can set up some kind of dumbbell situation where you have a long neck, and you can imagine that the first eigenvalue looks sort of constant in one ball, constant in the other ball, and then sort of interpolates in between with small energy. That's little neck. Okay. Alternatively, we can ask if given a, say, fixing just the topological type of the surface, can we find a sequence of metrics which make these scale invariant eigenvalues blow up, go to infinity? If we ask an analogous question in higher dimension, the answer is yes. Okay, but it turns out for surfaces, the answer is no. Okay, and so the first observation along these lines goes back 50 years to Hirsch, who showed that for any metric on S2, we have that the area normalized first eigenvalue of the Laplacian is always bounded above by 8 pi, which is exactly the normalized first eigenvalue of the round sphere. And moreover, equality holds only if we're isometric to the round sphere. Okay, so the proof is by now pretty classical, but let's just recall it because it'll motivate a lot of what we're doing subsequently. So first, by uniformization and the fact that S2 just carries one conformal structure, right? We know that we can always find some conformal diffeomorphism from the given metric to the standard one in our, right? But Hirsch's main observation is that we have some freedom in how we choose that diffeomorphism. So in particular, we can always post-compose that given diffeomorphism with some conformal automorphism of the standard 2 sphere, and that's a large group, right? Such that the components of the new map given by that composition, still a conformal diffeomorphism, satisfy this balancing condition. So these 3 scalar functions all have 0 average with respect to our given metric. Okay. So why is this useful? Well, we know by the variational characterization of the first eigenvalue by Rayleigh quotients, right, that if we have any function of 0 average, then its L2 norm squared times the first eigenvalue is going to be controlled from above by the energy. Right? So in particular, applying this to these balanced components of our conformal diffeomorphism, we have that, well, energy is bounded from below by lambda 1 times their L2 norm, right? That's just the definition of the first eigenvalue. But in particular, if we sum over I now, well, the sum over I of these psi I squareds, we're a sphere valued map, so that's just going to be 1. All right, and if we sum over I here, we're just going to get the total energy of that map. But that map is conformal, so this energy is going to be exactly twice the area of the image, which is just the area of the standard 2 sphere, so that's going to be 8 pi. And then since the sum over I of here is just going to be exactly 1, we just get lambda 1 times the area. So we get this really direct proof that the area normalized first eigenvalue is bounded above by 8 pi. And if we chase through what happens in the case of equality here, so this conformal diffeomorphism has to be by first eigenfunctions of the Laplacian, it's not hard to see that we have to be isometric. Okay, so that's Hersch's theorem from 1970. All right, so that's far from the end of the story. So a little while later, Yang and Yao observed that a similar balancing trick for conformal maps from higher genus surfaces to S2. So now we won't be looking at true conformal maps, right? Not diffeomorphisms, but weakly conformal maps. In particular, we can find by algebraic geometry branched covers, conformal branched covers of S2 by these higher genus surfaces. And in particular, we can estimate the degree of these covers in terms of the genus by algebraic geometry. And so they're able to get upper bounds in general on these first eigenvalues, just depending linearly on the genus of the surface. Right? So in particular, we see, in answer to this original question, that these first eigenvalues have a universal upper bound, depending just on the topology. Okay. All right, so now let's start defining some invariants from this. So let's say we'll fix a conformal structure, some conformal class on a given surface. So then we can define the conformal eigenvalues to be the supremum over all conformal metrics of this normalized kth eigenvalue. Right, so this capital lambda k, and that conformal class is just this conformal supremum. And then we can define the topological eigenvalues to be the supremum, not just over a fixed conformal class, but over all metrics on the surface. Right, so what we just saw of this Yang and Yao argument tells us that these will be finite quantities for any for k equals 1. But in fact, by work of Korovar from the early 90s, we know now that in fact these have to be finite for all k. Okay. So in particular, if we start looking at maximizing these quantities, these normalized eigenvalues, that's a well-defined variational problem. And it gives us kind of an interesting way of trying to find some kind of special metrics in our surfaces, which aren't given by any kind of curvature condition. So in the case of S2, we saw that we just got back sort of the round metric, but in general, it's not clear if we should get anything close to what we get from uniformization or other procedures for getting, say, optimal metrics. Okay, so that leads us to this isoparametric problem, which is first of all to compute these quantities, and then moreover to sort of characterize those metrics that maximize them. And since we can't say that we have maximizers in general, to at least get some picture of what happens to a sequence of metrics that saturate that bound. And we describe sort of the degeneration of the limit. Okay. So a little after the work with Yang, Li and Yao were able to refine Hersch's technique a little further. So instead of using balanced conformal maps into S2, they're looking at balanced conformal maps into higher dimensional spheres. This is really a key breakthrough, at least the introduction of the conformal volume. So the idea here is that similar to Hersch's trick, if we start from any branched conformal map from our surface into some sphere Sn, then you can always find again some conformal automorphism of that target standard sphere, such that all of the component functions of the composition are balanced with respect to our given metric. So the conformal group is large enough that we can always find such a map. And so in particular, by the same just summing over the Rayleigh quotients as before, we see that the area of the image, which by conformal conformality, right, has to be the same as the energy, where I'm using in my definition of energy here half the L2 norm of the gradient squared. We see that has to be bounded below by half of this area normalized first eigenvalue. Okay. So why is this useful? So well, first of all, we can take the supremum over all conformal automorphisms of the energy of this composition, right? And since we must have some conformal automorphism for which this holds, we have this inequality here, right? The supremum over all conformal automorphisms is bounded below by half this normalized first eigenvalue. And moreover, this holds for each branch conformal immersion, right? For any given map B from M into Sn to start with. And moreover, this holds for any metric G in that conformal class, okay? Because all of these energies are conformally invariant quantities. So what does this tell us? So this tells us that if we define, as Li and Yao did, this nth conformal volume of this conformal class to be the infimum over all these branched conformal immersions into Sn, of the supremum of the energy of its composition with the conformal automorphisms of Sn, then this quantity is going to be an upper bound for the normalized first eigenvalue. In particular, twice this quantity is an upper bound for the normalized first eigenvalue over any metric in this conformal class. Okay, so we have this natural conformal invariant. And moreover, it's a little more work than it was in Hersh's inequality, but not too hard to see, that equality holds if and only if G is induced by a minimal immersion into Sn by first eigenfunctions. Okay, so this connection that there's some relationship between maximization of these eigenvalues and minimal immersions into higher dimensional spheres, that's was a key observation. And so an immediate consequence of this was, well, it's not hard to see that this canonical Veronese minimal embedding of RP2 into S4 is mapped by first eigenfunctions of the round metric on RP2. So by the Liao theorem, we see that in fact the round metric on RP2 is also going to maximize the normalized first eigenvalue among all other metrics. Okay. And though it's not as relevant to the story we're talking about today, right, this conformal volume also gives a lower bound for the Willmore energy of all conformal immersions into Sn. Okay, so in particular, it links maximization of this lambda-1 bar quantity with minimization of W. We're not going to be talking much about Willmore energy today, but this is a very important feature of the conformal volumes. Okay. Great, so we're in the 80s now, and we've computed this normalized first eigenvalue max for S2 and RP2, where we only have one conformal class to deal with anyway. Okay, so let's go to a surface of higher genus where we have some more conformal classes to play with. So back in in 73 now, Berger was reading, I think, Hersh's work, and got interested in this question of maximizing the first eigenvalue in the torus. And so by playing around just with the flat metrics, he was led to conjecture that the maximum should be achieved by the flat equilateral torus, right, where we're taking C and modding out by the lattice generated by 1 and then a half plus root 3 over 2 is I, right? So we have our fundamental domain is this rhombus. Okay. So while Li and Yao's results show us easily that this metric maximizes its conformal class because we can find a minimal inversion by first eigenfunctions into the 5 sphere, it's not clear a priori that it maximizes among all metrics, right? We only know that it maximizes among conformal metrics. So the full conjecture remained open until the mid-90s, about 25 years ago. Okay, but then in 96, Nadarashvili came along and proved this conjecture. So he showed in particular that the topological supremum of the first eigenvalue in the torus is exactly 8 pi squared over root 3. It's given by the equilateral flat torus. Okay. So the proof is kind of distinct from these previous proofs for S2 and RP2 because it actually relies on the existence theory for maximizing metrics. So what was the idea? So first, Nadarashvili gave this analytic argument to argue that the maximizing metric does in fact exist. Okay, and then he showed, and this was sort of observed in some forms by Berger back in the 70s even, that any such maximizing metric has to be induced by a minimal immersion into Sn by first eigenfunctions. Okay, so now we reduce this to a problem of studying minimal immersions of tori into spheres by first eigenfunctions. And this was actually solved earlier, this classification of these objects by El-Soufi and Elias. So by El-Soufi and Elias, we know that in fact the only possibilities are the equilateral torus T2 into S5 and the Clifford torus T2 into S3. And then it's just a matter of comparing lambda-1 bar for these metrics, right? So this was the path to Nadarashvili's Berger's conjecture. Okay. So this then stimulated a lot of work understanding the existence theory in general. Okay, so now there's sort of a big literature has grown up around this problem of determining when the maximizing metrics exist, what do they look like, and when they don't exist, what happens in the degeneration. Okay. And both the conformal problem and the global problem are very interesting. So let's focus on the conformal problem first. So the first person to resolve this was Petrides, I think around 2014. Now there's sort of various other groups floating around, but this was sort of the first big positive result. So we have the following setup. So for each conformal structure on a closed surface, we know that if the kth supremal eigenvalue conformally is strictly greater than the k-1 eigenvalue plus 8 pi, and in fact, non-strict inequality always holds. So as long as equality doesn't hold, then there exists a harmonic map into Sn for some n, which you can determine, whose energy is exactly half this kth eigenvalue, and such that the metric given by, we can just choose a conformal metric which views the energy density of this map as constant. That metric is going to maximize the normalized kth eigenvalue in the conformal class. Okay, so in particular, with respect to this metric G bar, the coordinates of B are first eigenfunctions. Now I've put metric in scare quotes here because, of course, this map a priori, this harmonic map, can't have zeros, in which case, this is not an honest metric, right? But fortunately, I mean, we know what the zeros of the gradients of harmonic maps look like, and somehow at worst, this is a metric with some finite number of conical singularities corresponding to the zeros of that of D phi. Okay. So in particular, for the first eigenvalue, Dirichlet showed that this strict inequality, which in this case just says that lambda1 is strictly greater than 8 pi, always holds. Right? And this is a key result here. I mean, it's somehow analogous if you're interested in Imave type problems to the Aubin-Chain estimate, right? Telling us that if we're not on the round sphere, our Imave invariant has to be strictly less in that case, right? So here, this is somehow telling us that as long as we're not the round sphere, then our conformal first eigenvalue has to be strictly greater than that of the round sphere. This is going to prevent some kind of bubbling degenerations when we take a maximizing sequence. Okay, so in particular, maximization of lambda1 bar is going to work, and it's going to associate to each conformal class some distinguished harmonic map into Sn. Okay, when k is 2 or higher, so we're looking at higher eigenvalues, then in fact it is possible for equality to hold in that lambda k is lambda k minus 1 plus 8 pi, and this corresponds to some kind of bubbling behavior. This is something that is observed in cases. So for instance, the maximizers for the second eigenvalue on S2 or RP2, and in fact higher eigenvalues as well, you know to have this kind of bubbling behavior. Oh, let's see, there's a question in the chat. What is dimension n in these results? Okay, great. So there's classical results going back to the 70s and 80s, I think starting with work of Chung. I think maybe some of our organizers were involved in this as well, where you can estimate the maximum multiplicity of kth eigenfunctions for a surface in terms of its topology. Okay, so these n correspond to, I guess, 1 plus, or no, 1, the maximum multiplicity of the kth eigenfunctions minus 1. Does that answer the question? Great. All right. So that's the existence theory in the conformal case. Right. So if we have the existence theory in the conformal case, well, that reduces the global maximization problem to sort of a maximization problem over Teichmuller space now. So in particular, it's a finite dimensional problem. Still very non-trivial. But for k equals 1, Henrik Matthias and Anna Ziffert were able to show compactness for a maximizing sequence of conformal classes. So the key point here is they're able to rule out somehow degeneration to the boundary of Teichmuller space. And combining this with the conformal existence results, they're able to show that in any closed surface, there in fact does exist a globally lambda1 maximizing metric. Again, this may have some conical singularities corresponding to zeros in these maps, induced by a branched minimal immersion into a sphere by first eigenfunctions. Okay. So we have the existence result for lambda1, and it's not really well understood yet, the global existence problem for higher eigenvalues, again, because you have bubbling issues, and then for the global setting, you can also have you can imagine other generations happening in Teichmuller space. I think it's not really understood yet what we even expect maximization problem to look like for higher eigenvalues in cases other than S2 and R2. All right, so in particular, we see that for every conformal structure on a surface, maximization of these lambda k, as long as we don't have these bubbling phenomena, is going to give rise to some harmonic sphere-valued map whose energy corresponds exactly to the half of these conformal supremum, these eigenvalues. And moreover, from this harmonic map, we recover the maximizing method. Okay, so there's intimate connection between harmonic maps and these maximizing metrics. So recall, I'm using this term harmonic, I should be familiar to everyone here, but recall that a sphere-valued map is harmonic if and only if it's a critical point of the Dirichlet energy among maps restricted to take values in the sphere, right? And so equivalently, in equations we can express this in the fact that Laplacian of V is given by the energy density squared times V. And remember, of course, that in dimension 2, right, the Dirichlet energy is a conformal invariant, and so this harmonic map, being a harmonic map, is a conformally invariant property. Okay, so this somehow doesn't see a specific metric in dimension 2, just the conformal class. Okay. All right, so if they're critical points of the Dirichlet energy, then we know that these harmonic maps in principle should arise from some kind of variational methods for the energy function on the space of sphere-valued maps. So it's kind of clear from immediate considerations they won't be minimizers, but we can hope that maybe these arise from some kind of force theoretic or min-max methods. And that was the question that sort of initially led to this collaboration with Mikhail Karpukhin, which is just this innocent question of whether these harmonic maps associated to maximization of these eigenvalues can in fact be produced by some sort of natural or canonical variational methods for the Dirichlet energy, these sphere-valued maps. Okay. And initially this is just kind of a curiosity. If we have these critical points of the Dirichlet energy arising naturally for geometric reasons, one would hope to have some nice characterization of them. But of course, we've seen over the last decade, especially with the resolution of the Wilmore conjecture, that having variational characterizations of some nice critical point in geometry, right, sometimes gives us more information, than we were initially hoping for. So let's see. So that's part of the idea. Okay. So for the first two eigenvalues of this first paper, we were able to say the answer is yes. So we can relate these conformal supremum for the first and second eigenvalues to some natural min-max problem for the Dirichlet energy on the space of sphere-valued maps. And using this min-max characterization, we're actually able to get some slightly stronger properties for these conformal maxima. Okay, we'll come to that in a moment. Let's see, any questions so far? Okay, let's plow ahead. So let's see, I'm going to focus on the first eigenvalue, and that's what makes it prettiest. So what's the min-max characterization of this first conformal eigenvalue? So let's consider the following setup. So if n is at least 2, we think about maps to the 2-sphere or higher, we're going to consider a weakly continuous family of maps parameterized by the closed n+1 ball, right? So sending points in the closed n+1 ball to maps in W12 to the n-sphere. Okay. And we're only requiring they be weakly continuous. They need not be strongly continuous as a map from B N+1 into W12. And they satisfy this boundary condition that f sub a is exactly the constant map to A when A is this boundary point in the n-sphere. Okay, so in particular, as an exercise, if we require that this were continuous, say as a map to C0, then no such family could exist. And if we required that it were strongly continuous to W12, a harder exercise would be to show that again, no such family exists. Okay. So what's an example, since I just told you that if we put too many continuity constraints, these guys don't exist. So for instance, one can take f sub a to be g sub a composed with phi, where phi is some branched conformal immersion that we're fixing from our surface into Sn. And g sub a of x, well, this is a family generating the conformal automorphisms of Sn modulo isometries. So in particular, modulo rotations of Sn, this class of families is going to include these families whose min-max energies Li and Yao used to define the conformal volume. Okay. Well, for any such family, just going back to this general setup now, if we take the map sending a point in Bn+1 to the average of that map as a vector in Rn+1, well, then it's easy to see that it's continuous, right? Because these are weakly continuous functions of beta fa. And moreover, it obviously by this boundary condition restricts the identity from the boundary Sn to itself. So in particular, just by elementary topology, there must be some A in the interior of that ball for which the coordinates of this map fa are balanced. Okay, so we're just replaying Kirchner's greatest hits here. All right, so in particular, for any such family, right, we see that right for this point where we have balancing, then again by Hersch's trick, this lambda1 times area is going to be bounded above by twice this energy quantity. So in particular, if we define a min-max energy to be the infimum over all such families F, of the supremum over all A in the ball of the energy, then we see that, well, for any metric, this normalized first eigenvalue is going to be bounded above by twice this energy, this min-max energy. Again, just because we always have some point A in the ball, which is inequality holds. And moreover, well, these energies, since the Dirichlet energy is conformally invariant, it's clear these min-max energies are also conformally invariant. So we end up with this conformal invariant sits in between half this normalized first eigenvalue and the conformal volume. Okay, so in particular, whenever we have equality in Lie-Gauss inequality for the conformal volume and the first eigenvalue, then we'll have equality for this min-max energy as well. But in general, we just know that it's going to sit somewhere in between. So in practice, for analytic reasons, we opt for a slightly different definition, because if we're actually trying to carry out min-max methods for this sort of Dirichlet energy, which is a formally invariant functional without the Laplacian condition on this space is weakly continuous maps into W12, then somehow classical min-max methods would not deliver us a critical point. But somehow there's a nice relaxation procedure via Ginzburg-Landau type perturbations, which I won't get into for the purpose of this talk, but it's easy to sort of come up with a slight tweaking of this definition such that it satisfies all the same properties and actually gives us a critical point. Okay. Right, so in particular, after tweaking slightly the definition of these min-max energies En, it's not hard to see that the min-max energies are in fact achieved by a harmonic map, possibly together with some bubble tree of harmonic maps from S2 and S2. So we have the following to start with. So for every n at least 2, we know that there's going to exist, and for any fixed conformal structure, we know there's going to exist some harmonic maps from M into Sn, and some possibly also some harmonic maps from S2 into Sn, some bubbles, such that the total energy realizes this min-max energy that we defined. And moreover, we have this Morse index bound, so we have this n+1 parameter min-max, and we can show that as critical points of the energy functional, the Morse index of this all of these maps together sums up to less than or equal to n+1. Okay. So all right, so we have this energy achieved by some map, possibly with some bubbles. But in fact, we can say a little more if n is sufficiently large. Okay, so first of all, we have this classic result by Iosif, which tells us that for any non-trivial harmonic map from a surface into Sn, its energy index, Morse index, is at least n-2. Right, and the equality implies that you're in fact an equatorial S2 sitting inside Sn. All right, so by the sort of classical structure theory for harmonic maps from S2 to Sn, and some subsequent work by my collaborator Mikhail Karpukhin, we know in fact that if we have a harmonic map from S2 to Sn, and the Morse index is at most n+1, then B has to be an equatorial embedding. So not only does being n-2 imply that you're an equatorial embedding as in this Iosif theorem, but if your domain is actually S2, then there's a larger gap. Okay. And finally, this result of Petrides, which I mentioned before, which tells you that if M has positive genus, or is also RP2, or something orientable, then this normalized first eigenvalue in the conformal class, the supremum is strictly greater than APOC. Okay. So putting this together, well, what do we know about our maps? We know that the sum of their energies is bigger than or equal to this half this normalized first eigenvalue, which is strictly bigger than 4 pi. So we can't have the situation where we have just one equatorial bubble, okay, because that would violate the Petrides inequality. However, this inequality of Iosif, well, since we're bounded above by n+1 in the total index, and each map should have index at least n-2, it's clear that for n sufficiently large, we'll have at most just one bubble, or just the map we were looking for. Okay, but if we have just one bubble, then finally this result of Barbosa and Karpukhin and various other people tells us that if the energy index of that bubble is at most n+1, which we know it has to be, then it's equatorial. But we just said that can happen by Petrides inequality. So to make a long story short, for every conformal structure, other than the round sphere, the round sphere is covered by classical methods, we see that if n is in fact strictly greater than 5 is large enough, then there exists a harmonic map M to Sn achieving this min-max energy of index, Morse index at most n+1. Okay, so it's not just achieved by maplets and bubbles, but in fact for n sufficiently large, it's achieved by an honest harmonic map. Okay. Great. So now we would like to show that if n is sufficiently large, so this in general should be larger than just this 5, then in fact we have equality here. So this in fact is not just some harmonic map, but is in fact the harmonic map realizing the maximal metric of the lambda 1 of this class. Okay, so what's the idea? So for these harmonic maps, notice we can again consider these associated metrics. And again, these aren't quite metrics around the zeros of the maps, but that doesn't really matter too much, which view their energy density as constant. So in this metric, just by looking at what the harmonic map equation says, the components of Bn of this map are going to be Laplace eigenfunctions with common eigenvalue lambda is 2. Okay. So one can define this quantity called the spectral index, which just tells you where this eigenvalue 2 falls in the spectrum of the Laplacian for the degenerate metric. Okay, and so equivalently, this has a conformally invariant definition, where for any g in this conformal class, it's just going to be index of the Schrodinger operator given by Laplacian minus the energy density. Okay, so why do we care about the spectral index? Well, if k is the spectral index, then we know that lambda bar k is exactly twice the energy density, or excuse me, twice the min-max energy, which we know is bounded below by this capital lambda 1. So if we can show that k is 1, that the spectral index is 1, so 2 is the first eigenvalue for the Laplacian of this metric, then in fact we have, by definition of this supremum, that bar lambda 1 is bounded above by this capital lambda 1 as well. And we end up with this desired inequality. The min-max energy is exactly, there's a 2 there, that should be a 1/2. The min-max energy is exactly 1/2 of this conformal supremum of lambda 1. And moreover, these maps are the ones whose metrics achieve the maximum. Okay, so how could we go about doing that? So to show that this index is 1 for n sufficiently large, we first know that these energies are non-increasing in n. That's easy. And then there's a technical part we deduce by a contradiction argument. I put a star here, so I have a footnote later. That there exists some n, depending just on the conformal class, such that for all little n sufficiently large, maybe we should use 2 letters there, that these Sn valued maps are given by harmonic maps into a lower dimensional sphere whose dimension is fixed by the conformal class, and then just the equatorial embedding of that lower dimensional sphere into Sn. So what we're saying is, in fact, more generally, what we prove is that if we have a sequence of harmonic maps into spheres whose dimension a priori is going to infinity, then in fact, if there's a uniform energy bound, then they in fact have to all lie in a lower dimensional sphere of fixed dimension. Okay, so energy bounds somehow imply that it bounds on the dimension of the target. Okay, so that's a lemma. More technical one for the paper. Okay, so now if we take this for granted, and if we compare the Morse indices of these maps, so the full map Bn to the higher dimensional sphere, and then the Morse index of this map to the lower dimensional sphere, then one finds that the difference is going to be exactly the difference from little n and this fixed big N of the spectral index of this map piece of n. Okay. So in particular, just forgetting about this Morse index, this psi n part, because we know that's at least non-negative, right? Then we know that n+1. We know that by the min-max characterization, right, that's going to be bigger than or equal to this Morse index of the Bn. But we see that's bounded below by little n minus this fixed big N times the spectral index of n. So in particular, if the spectral index is 1, or excuse me, if the spectral index is larger than 1, we would get a contradiction as soon as little n is bigger than this fixed 2n+1. Okay, so in fact, the spectral index has to be 1, and we get this desired equality. So returning to the star here, just want to say, so our contradiction argument for proving this lemma, we assume we have a sequence of maps that has this behavior. So we have, taking values in higher and higher Sn, and they're not taking values in a lower dimensional sphere. So a particular dimension of the space spanned by their coordinate functions is going to infinity. Well, then this somehow tells you that these Schrodinger operators associated with these maps have kernel whose dimension is going to infinity. But then by some bubbling analysis, you can say that you can arrive at a Schrodinger operator on, say, the original surface, maybe union some spheres, who also has to have all of its spectrum collapse below 0. Right? But then you can show that the Schrodinger operator is nice enough so this doesn't happen. Okay, so it's kind of a fun argument, but it would be nice, and I think in principle, some such argument should exist, but we didn't find it, to get an effective geometric proof of this stabilization property of harmonic maps of bounded energy. So given an energy bound, can you say sort of what the maximum dimension is of the target sphere in which you're linearly full? I think it's an interesting problem that we thought about briefly as we were doing this, but then we had the ugly argument that worked and eventually just thought ahead with that. All right. So now we know this this thing we set out to prove, right? So for n sufficiently large, these min-max energies are in fact exactly half of these conformal supremum, and moreover, the metrics associated with these min-max harmonic maps are exactly the ones that maximize this lambda 1 bar. Okay, so that's fun to know. So we also find some similar min-max characterization for lambda 2, but the construction doesn't seem quite as geometrically natural. So somehow it works for all the applications we have, but I'm not going to bother presenting it here because I don't think ultimately it's the right way to think about this for generalizing it to higher eigenvalues. And I do believe this should work for higher eigenvalues. Okay. I'll mention that in that case, though, we do expect bubbles in general. So these lemmas about just having a single harmonic map, now instead we'll have a harmonic map together with some bubbles that we can characterize, the higher eigenvalue problem. I'll stick to just the first eigenvalue. All right, so you know, as a byproduct, we get a new proof of the existence of these maximizing metrics. Okay, but in fact, we get a little bit more. So before I go on to the questions. Okay. All right, so if we're looking at the variational theory for these normalized eigenvalues, then one of the first things you realize if you're trying to, say, solve the maximization problem by direct methods is that it's natural to try to extend these notions of you know, first eigenvalue to Laplacian to metrics of lower regularity, right? So in particular, since conformal metrics of fixed area just correspond to, say, smooth functions, smooth positive functions of fixed L1 norm, then you're naturally led to consider some kind of spectrum, generalizing the Laplacian spectrum to the weak closure of these guys. So in particular, to non-negative radon measures. Okay. So given some conformal class and some radon measure on our surface, we can define a first eigenvalue, which is generalizing the first eigenvalue of Laplacian, by just this the same Rayleigh quotient definition we had before, where now the only difference, right? So the Dirichlet energy term, that's a conformal invariance that just depends on our conformal structure. But now we ask that we have zero average with respect to that measure mu, and that the L2 part of the Rayleigh quotient, the denominator, right, is now L2 with respect to this given measure. Okay. And then given these first eigenvalues, we can also define these normalized first eigenvalues. So we just normalize by the mass of that measure, right? Okay, and I'll note that you know, a similar characterization works for higher eigenvalues as well. So you get a min-max characterization via the Rayleigh quotients. Okay. All right, so in particular, right, if mu is just the, say, rho squared times the volume measure of a fixed metric, or rho is just some positive function, then we recover just the Laplace eigenvalues, this conformal metric, rho squared. Right? But the definition is a little more interesting than just this. It includes some other sort of natural geometric spectrum. So one of the most important examples is from the Steklov spectrum. So if M is a surface of boundary, and mu is just the length measure of that boundary, then this first eigenvalue applied to that measure mu is exactly the first Steklov eigenvalue of mg. So that is the first eigenvalue of this Dirichlet and Neumann map, where we take a function of the boundary, take its harmonic extension, and then send that to its the normal derivative of the harmonic extension of the boundary. Okay. So not only is this a classical spectrum of some nice geometric pseudo-differential operator, but in fact it has a nice story similar to the story of maximization for Laplacian eigenvalues. So this is more recent, but within the last 10 years or so, maybe a little longer, Fraser and Shane started this program of studying the variational theory for these Steklov eigenvalues normalized by the length, okay, on surfaces of a boundary. And in particular, they showed that a maximizing metric has to be induced by a free boundary minimal immersion into some Euclidean ball. Okay, so it's an interesting analogy with the maximization problem for the Laplacian spectrum on closed surfaces. We're getting minimal immersions into spheres in the maximizing case. Okay. And in fact, just last year, the existence of maximizing metrics for these sigma 1, corresponding to some branch free boundary minimal immersions, was finally confirmed by Matthias and Dirichlet. Okay. There's an interesting analogous story on surfaces of the boundary that fits into this eigenvalues and measures framework. Okay. All right, so if we have an arbitrary radon measure now, then these substitute for the Laplacian spectrum can be very badly behaved. So for instance, if we have just a Dirac mass, the first eigenvalue is infinity. That's not going to be very useful for maximization problems. And if we have, say, something like a Dirac mass plus an absolutely continuous measure, the first eigenvalue is going to be 0. Okay, so if we just take measures willy-nilly, we'll get some strange things popping up. Okay, but let's consider a type of measure for which the spectrum will be sort of well behaved and what we would expect from a Laplacian spectrum. So we'll call a radon measure mu admissible if the natural map from, say, C1 of M into L2 of that measure extends to a compact map. So in particular, continuous, but also compact map from W12 of our ambient space into L2 of mu. Okay. So, right, so for just the usual volume measures, this is just the standard package results from Sobolev spaces. But moreover, let's say if mu is this length measure on the boundary, and this is compactness of the trace map, W12 into L2 of the boundary. So it contains a lot of these actual real geometric cases that we care about. Okay, and it's you know, an elementary exercise in functional analysis. The spectrum of such a measure is sort of what we would expect from the Laplacian spectrum, right, or a spectrum of a nice pseudo-differential operator. So it's going to be in particular non-negative, discrete. It's going to go to infinity as k goes to infinity. And moreover, the eigenvalues are realized by some eigenfunctions. Right? So this is what it means to be an eigenfunction for these measures. Okay. So in particular, these are somehow the natural measures that we really expect to see something that behaves like the Laplacian spectrum. All right, so what we show using the min-max characterization is that, in fact, for any admissible mu's, any mu satisfying this criterion, we have that the normalized first eigenvalue is bounded above by the maximum conformal eigenvalue over the smooth metrics. And moreover, equality holds only if mu is a smooth maximizing metric. Okay, so a priori it wasn't clear, right, whether these maximization problems, these admissible measures, give you something different, something of you know, with the larger eigenvalue. So we show not only is it bounded, but in fact we have this rigidity, or if you like, a regularity result, which tells you that an honest maximizer has to in fact be a smooth maximizer. Okay, and maybe I'll note that if you look at sort of just critical points, this normalized first eigenvalue measures, you can get things that aren't smooth. So it's not as though you can expect to get a regularity result just by looking at sort of you know, the critical point condition and deriving some regularity theory. It's really the regularity fact here is strictly for maximizers. Okay. So this has some implications for the Steklov problem. I'll come back to that towards the end of the talk. First, let's pop over to more recent application of the min-max characterization, which is a question, you know, so we've looked at variants of these questions, I think, already in this conference, where we have a nice rigidity result in geometric analysis. We often want to know if we have any flexibility or stability, right? So if we know that, you know, in this case, some maximizer for a geometric quantity has a nice strict characterization, can we say that if we're close to being maximum, that we're somehow close to the maximizer, right? So in this case, let's say if you know, we have a metric, or more generally one of these measures, which the first eigenvalue is close to the conformal or the global maximum. Is there any nice sense in which we can say that we're close to the maximizing metric, right? The maximizing metric. Okay. And so we do get a positive answer. So when we find out that the correct notion of distance will come from this W-1, 2 norm. So in other words, the W12 dual norm on, say, the space of measures for an appropriate choice of background. So for instance, for S2, for the classical Hersch inequality, we get the following quantitative version. So this is with Mikhail Karpukhin, Mikhail Nahon, and Iosif Polterovich. So if we take, say, the standard metric on S2, then for any admissible measure, we normalize the first eigenvalue to have 2, so just rescale it so this is true. Then there exists some conformal automorphism of S2, such that 8 pi minus the normalized first eigenvalue, so the gap, the distance from being maximum, is bounded from below by twice the conformal push forward of mu by this conformal automorphism times minus the area measure of this the standard metric in the W-1, 2 norm for the standard metric, and then we'll square. Okay. So I'll describe in a moment why this holds. And in fact, this doesn't require the min-max characterization. It just requires squeezing a little bit more out of the classical Hersch. But let me comment for now that both the space W-1, 2 and the exponent 2 are optimal. Okay, so when I say the space W-1, 2 is optimal, if you look at any of sort of the familiar Sobolev spaces, this is the best one in which this inequality holds. So it's possible there's some more exotic space unrelated to Sobolev spaces where you can get a similar estimate. But as far as we know, among sort of the layman spaces, this is the seems to be optimal. Okay. So we're able to get some similar quantitative stability theorems for the global maximization problem on RP2, on the 2 torus, and on the Klein bottle. And in particular, these are all the topologies for which the maximum has been determined, except for the genus 2 case, where the maximum is degenerate and it's realized by a branched cover of S2. So in the genus 2 case, somehow these inequalities of Yang and Yao are actually the ones that achieve the maximum. And that one somehow isn't really amenable to our method as far as the quantitative inequalities go, which is strange. But so for instance, we can make Nader-Ashvili's theorem quantitative by saying that for any metric G on T2, there exists a metric G not isometric to the equilateral torus, such that the given metric normalized by first eigenvalue is within the gap from the canonical metric, the equilateral metric, right? This inequality here. And moreover, you can replace this, I'm phrasing this for a metric G, but you can also replace this with a conformal class and some measure, right? So we can weaken the requirement to be an honest metric. Okay. So for a general conformal structure, or for a general surface, where we don't have the examples explicitly, we don't have the quantitative stability in general, although we expect it should hold in many examples. But we do have the following qualitative stability result. So let me mention that, it's not clear a priori from anything I've told you so far, and in particular, I'm not sure it was even believed by experts for a while, that if you take a maximizing sequence of metrics, or say a maximizing sequence of measures, that you actually get general convergence, even in the weak sense, to an honest maximizer, right? So it's not clear that sort of a naive direct method would actually produce a maximizing metric in general. So, but it turns out it does. So if we fix a background metric, doesn't matter which, just fix one in the conformal class. Then for any sequence of admissible measures, which the normalized first eigenvalue approaches the maximum, then though we don't estimate the rate in general, we can say that in fact these measures will converge in W-1, 2 to the maximizing measures, in particular the volume measure of the conformally maximizing metric. Okay. And okay, so let me now finally say a little bit about the proof. So to cover the case of arbitrary conformal class, we need this min-max characterization. And the output of the min-max characterization that's relevant here is that for any admissible measure mu, we can say that there exists a sphere-valued map to a sphere of fixed dimension based on the conformal structure, whose mu average is 0, and whose energy is bounded from above by lambda 1. Right, so here we're using the fact that this min-max characterization, we said that, by virtue of how the min-max families were set up, for any given metric, you could always find a map with 0 average. But that's true if you replace that metric by some measure. We can always find for an admissible measure one of these maps such that it has mu 0 average. And then since these min-max energies correspond to this lambda 1 for n sufficiently large, that's where this result comes from. Okay. Again, just very strict. Apply to this min-max characterization. So why is this useful? So for such a map U, for any v, say in W12 of m to Rn+1, we can see that the difference of the L2 pairing of the derivatives of du and dv minus the first eigenvalue of mu times just the pairing of u and v with respect to d mu. So, right, so this quantity which would vanish if and only if u were first eigenfunctions for this measure mu is bounded from above by, well, first of all, the derivative of v and L2 for that given test map, and then the square root of the gap of the energy of the map U from the first eigenvalue of the measure. Right, since it's balanced, we know that this is non-negative. But moreover, since we have this inequality, we know that this gap is bounded from above by the gap that we want to measure between a lambda 1 bar and the maximum lambda 1. Okay. So, and this is not really a deep inequality. If you play with it, you'll realize that in fact it's just an application of Cauchy-Schwarz essentially. If you restrict to v of 0 average, then this becomes a non-negative quadratic form, and it's easy to see where this comes from. So this is a straightforward inequality. And if we apply it to cases where the maximizer is known, we have explicit maximizers, and we sort of understand how these maximizers sit inside nice families like the conformal families of B and Yao, or the conformal automorphisms used by Hirsch, then just sort of plugging those families in gives us these quantitative inequalities. In general, for an arbitrary conformal class, we have to use the existence of these maps, which is a consequence of the first min-max characterization. And so then this tells us that, well, okay, we have a maximizing sequence, then we get this corresponding sequence of maps, which in some weak sense are looking like first eigenfunctions for these measures. And in particular, it follows with a little work that they're going to converge weakly. This is a harmonic map. And then if you dig into the bubbling analysis, so what's happening with energy concentrates, then using the fact that they're almost first eigenvalues, almost first eigenfunctions, it's not just enough to know that they're, sort of a Laplacian sequence for the energy, because those can be quite poorly behaved in general. But because they're almost first eigenfunctions, we can then show that they in fact have to strongly converge to one of these harmonic maps associated to the maximization problem for lambda 1. And it's not hard to deduce then from this inequality again that forces the measures to converge to one of the maximized measures. Okay. And okay, so we're also then able to get similar W-1, 2 convergence results, the globally maximizing case. And in that case, we don't really have to do anything new on the qualitative side, because now we just combine this compactness result in the conformal class with the compactness results for maximizing conformal classes by Matthias and Ziffert. So now we don't have to add too much new there on the analysis side. All right. So those are some of the main contributions of this recent paper, which came out this past week. So this is kind of, a satisfactory answer to this little analytic question about if we have, not the eigenvalues close to the maximum, is the associated metric close to the maximum metric? So we get kind of a more or less complete answer for this stability for the isoperimetric inequality, these first eigenvalues. And in fact, for the second as well, although now things get more complicated because again, you have these bubbling phenomena. So the results don't look quite as nice, but somehow we get the output that the behavior of an arbitrary maximizing sequence mirrors that of sort of the distinguished maximizing sequences found by Vitridis and others. We can describe the degeneration into sort of bubbles in a precise way. So the first eigenvalue case is cleaner to state. Okay, so that's the story there. So all right, so this kind of analytic results, let's take it back to something nice and sort of classical in geometry. So let's go back to the Steklov maximization problem. So let's note by sigma 1 of gamma r, say the supremum of the normalized first Steklov eigenvalue over all metrics G on the surface of genus gamma and R boundary components. Right, so by Fraser-Shane and Matthias and Vitridis, we know these are going to be achieved by some free boundary minimal surfaces in Euclidean form. Okay, so as a consequence of this rigidity regularity theorem for admissible measures in the first paper, if we're applying it to the length measures for appropriate collections of curves inside our closed surfaces, it's not hard to show that this first Steklov eigenvalue for genus gamma and any number of boundary components is strictly bounded from above by lambda 1 of gamma. Okay, so the maximization problem for Steklov for a fixed genus and any number of boundary components is always bounded above by the Laplacian maximization problem for the same genus. Okay. So on the other hand, around the same time last year, Alexander Girouard and Jean Lagacé showed that by homogenization construction, that one can always find, say, in any given fixed surface, say, a sequence of domains inside by sort of excising a large collection of disks that are whose total area is going to 0, but they're becoming dense in an appropriate way. You can find a sequence of domains whose Steklov spectrum converges to the Laplacian spectrum. And so as a result, we're able to conclude that the limit of these Steklov maxima, sigma 1 of gamma r, as r goes to infinity, as the number of boundary components goes to infinity, is bounded from below by lambda 1 of gamma. And so in particular, combining those two statements, we see that this the sigma 1 of gamma r, this Steklov maxima, are converging as r goes to infinity to the this global maximum for the first Laplacian eigenvalue. Okay. So once these results started coming out, a folklore conjecture quickly sort of grew up, which said that, okay, well then if this is the case, we have this convergence at the level of the numbers of these spectra, then maybe the maximizing metrics should also converge, right? So you can ask if the Steklov maximizing metrics, these free boundary minimal surfaces corresponding to the sigma 1 and gamma r, in fact limit in any reasonable sense to the lambda 1 maximizing metric on the closed surface of genus gamma. As R goes to. Okay, and building on these stability results with Nahon and Polterovich, Mikhail Karpukhin and I have been able to say this is true. So the free boundary minimal surfaces in BN+1, which achieve this maximum sigma 1 of gamma r, converge at least as varifolds as R goes to infinity to the closed minimal surface in Sn, realizing lambda 1 of gamma. Okay, so try to make a few remarks here. So being a minimal surface, free boundary minimal surface in the ball, a priori looks very different from being a minimal surface in the sphere, the boundary, right? But in fact, both satisfy the condition that if you push them around by diffeomorphisms of the ball, which fix the boundary sphere, then they're going to be critical points for the area functional under those kind of perturbations. And that's why you're allowed to sort of achieve these closed guys in the sphere as varifold limits of free boundary minimal guys. On the other hand, it's immediately clear that we can't expect anything as good as, say, C1 convergence, even if we can fill in these boundaries in some clever way, because they're going to be orthogonal to the boundary sphere. They're converging to something which is tangent to it. So we have this varifold convergence. We can't get anything as good as C1 convergence, because that's simply ruled out a priori. Of course, it'd be interesting to know if one can sort of refine these things. So what's the idea here, right, is we are somehow able to conformally identify these sigma 1 maximizing surfaces of boundary with domains inside the closed surface. And then using the global stability result, we're able to say that the boundary length measures have to converge in W-1, 2 to the volume measure of this maximizing metric. Okay. And then we use this together with the sort of basic properties of these free boundary minimal surfaces and the limiting guy to show, right, that the extensions, the harmonic extensions of these free boundary minimal surfaces to the disks now inside this closed guy, the harmonic extension is going to converge strongly in W1, 2 to the maximizing map that we want, the minimal immersion achieving maximum value for the Laplacian eigenvalue. Okay. So as I mentioned, it would be nice to get a more refined picture of how this convergence happens. And in particular, that's true in the cases like S2, RP2, T2 in the Klein bottle, where we know explicitly what the maximizers are for the Laplacian problem. So if we can understand in sort of a refined way how this convergence happens, then we get the better and better picture of what the Steklov maximizers actually look like, which previously is sort of not really well understood at all. The Steklov maximizers are, I think, explicitly known only in a couple of cases like the annulus and the Mobius band. And I'll mention that when the genus is 0 or 1, and then we have a similar result for RP2 or K, using these quantitative stability results in the paper with Nahon and Polterovich, we can get some nice estimates on the actual gap between these Laplacian maxima and the Steklov maxima. So in particular, we take the gap between the Laplacian maximum and the Steklov maximum with the R boundary components. This is going to be bounded below by log R over R. We think this might be sharp. We're still trying to figure that out. Okay, so then finally I'll end with a question that's sort of unrelated to the spectral problems, but I think is an interesting one for anyone in the minimal surface side of things, which is given a minimal surface in the boundary sphere, under what circumstances can you find a sequence of free boundary minimal surfaces in the ball converging to it? Because again, somehow the convergence of these free boundary guys to these closed guys in the boundary sphere is kind of an exotic and interesting behavior. So we know this happens for the minimal surfaces arising from the Laplacian maximization problem now. But does it happen, for instance, for the lossy surfaces in S3? Can you find free boundary guys in B4 which converge to it, maybe by some pooling method or some clever variational scheme? I think that would be interesting to understand. All right, but I'll stop there for now. Thanks for your attention.
Thank you very much, Daniel, for this beautiful talk. Are there any questions? So there is one in the room from Baptiste de Viver. Please.
Thank you, Daniel, first of all, for the talk. It was really great. I have a very small question concerning the first theorem you spoke about for the min-max characterization by harmonic maps. Of the first eigenvalue in the closed case. Is there a similar thing for the free boundary case? Steklov?
So the short answer is no, in the sense that hasn't been thought about explicitly. My guess would be that there should be something similar, except instead of somehow harmonic maps into the sphere, you'd be looking at something like half harmonic maps from the boundary of these surfaces of boundary into the sphere. So somehow your functional is going to be map your boundary curve into the sphere, and then take the harmonic extension and look at the variational theory for that guy. And I would expect that something similar should be true and give you a max characterization of the Steklov guy, but I'm not sure.
Okay, thank you.
More questions? Okay, it doesn't seem the case. So thank you again for this very exciting talk.
Thanks for having me.
And so next talk is in exactly 30 minutes. Thanks, Daniel.
Thank you.